In section 3 of chapter 5, we're going to talk some more about work and heat, and we're going to introduce a new state function called enthalpy that will help us describe what goes on in chemical reactions. So let's start by talking more about work. The most common type of work that we encounter in chemistry is called pressure volume work. It's not the only kind of work, but for now in Chemistry 171, this is the only kind of work we're going to assume. Later on in general chemistry, we'll get to the point of introducing electrical work. That's another kind of work that we can get out of chemical reactions, the reactions that occur in batteries. But for now, we're going to talk about pressure volume work, and this is a very important kind of work because this is the work that takes place, for example, inside an internal combustion engine. When you burn gasoline, you expand gases, the gases push against a piston, and the work done is pressure volume work. So this is an extremely important type of work in everyday application. So we're going to define PV work as work equals minus the pressure times the change in the volume. And a natural question that arises when we do this is, why is there a minus sign in this definition? Well, it has to do with our definition of work. Remember, we've defined work as being positive if the energy is being added to the system. So work is always something done to the system. So if you think of a system being a gas in a container, if you squish the gas, if you compress it from a large volume to a small volume, you're doing work on the system. That's a positive work. And that corresponds to having a negative delta V. Remember, delta V is final volume minus initial volume. So if we take a small final volume, subtract a big initial volume, that corresponds to compressing the gas, that should be a positive work. But that's a negative delta V, so we introduce a minus sign. So the minus times the negative delta V times P, which is always positive, gives us a positive value for W. If, on the other hand, the volume of the system expands, then we say that the system is doing work on the surroundings, or the work done on the system is negative. We can see this in one of the drawings in the textbook. Here, what they're starting with as an initial state is a small volume. They're going to a larger volume for the system, so that's an expanding volume of the gas. So in this case, the volume change is positive. So the work here, W, is negative. And I have to point out that the book has an error here. The work done on the system is negative, so that the work done on the surroundings must be positive. So this is incorrect. The work done on the surroundings is necessarily minus the work done on the system. So that is P delta V, not minus P delta V. All right, so how can we put this together? We know that the change in energy is just the heat plus the work. This is the first law. That is, if the energy of the system changes, it must change due to a flow of energy from somewhere else. And there's only two types of energy flow, heat and work, and that's it. So assuming that our only type of work is pressure volume work, which is what we're going to assume for this course, I can replace the plus W with minus P delta V because, as we just saw, work is equal to minus P delta V. Now, if we look at the conditions under which we do chemical reactions, we really only have a couple choices. One choice is we could do chemical reactions at constant volume, that is, delta V equals 0. Constant volume requires a closed container that is rigid so that the volume can neither expand or contract. If we're at constant volume, if delta V is 0, then the delta V up in this term is 0. Pressure times 0 is 0. And therefore, under constant volume conditions, that's why we have a V here as a subscript on the Q, the heat at constant volume is just equal to delta E. That comes from this equation, replacing the P delta V with 0. If, on the other hand, we do a chemical reaction under constant pressure conditions, that is in open containers, open to the atmosphere, that's a constant pressure condition, then when we solve this equation for Q, we get Q at constant pressure is equal to delta E plus P delta V. I've just moved the P delta V over to the other side of the equation to solve for Q. Now the question is, which of these conditions best describes chemical reactions in the chemical laboratory? Well, at least in general chemistry, we do a lot of solution chemistry. We mix things in beakers, we use solutions in burettes, and every container we use is open to the atmosphere. And so the condition that we use experimentally is this one. It's not that we couldn't do chemistry in closed containers, it's just not our most common condition. So all I'm saying is that typically when we do benchtop chemistry, we're doing chemical reactions at constant pressure. So this is the form for heat that we use for benchtop reactions. The fact that benchtop reactions are constant pressure inspires us to define this new state function called enthalpy. So we're going to define enthalpy, which we always represent with an H, as the energy plus pressure times volume. So if we take a change in enthalpy, that means taking a change in this quantity, that's just how we've defined it, and that's the change in the energy plus pressure times the change in volume plus volume times the change in pressure. So that at constant pressure, which we've decided is most like our benchtop conditions, delta P is 0. So this term goes to 0 under conditions of constant pressure, and we arrive at delta H is equal to delta E plus P delta V, and that's an important equation for you to remember. Okay, the change in enthalpy is the change in energy plus P times the change in volume. Now it's often the case for many reactions, not all for sure, but it's often the case that this P delta V term is on the small side, especially if we're dealing with liquids and solids. The change in volume typically is very small, so we think of an enthalpy change as sort of a measure of the change in energy. It's close, but really what it is the amount of heat transferred under conditions of constant pressure. All right, so enthalpy is a state function. It's composed of state functions. It only depends on where we start and where we end up, and not on the details in between. And we've seen how that can be a very convenient feature. So what we're going to do now is define what we mean by the enthalpy change of a reaction. The enthalpy of reaction, our formal definition, technically unusable, and we'll get to that, is that the change in enthalpy for a reaction, remember, change in anything is always the final value minus the initial value. In a chemical reaction, the final state is the set of chemical products that we have. So formally, we take the absolute, notice there's no delta here, the absolute enthalpy of the products, we subtract the absolute enthalpy of the reactants, and that will give us what we define as the change in enthalpy for a reaction. Now this isn't really usable for the same reason that we don't really use absolute energies. We just can't measure it. We can't actually measure this quantity. But we can still measure experimentally the change in enthalpy because of its connection with heat. So the way we actually measure is we measure the amount of heat exchanged by a system, and doing that involves something called calorimetry, because we know the heat exchanged at constant pressure is equal to delta H. And we're going to talk about calorimetry at the end of the chapter. For now, let me just talk about some of the formal properties and definitions related to enthalpy changes for reactions. So if our enthalpy of reaction is negative, we say that Heat is a product of the reaction, so you can think of the heat as literally being coming out of the reaction. Again, what does this mean in terms of heat? If I define this, remember this is equal to the heat at constant pressure. So what we're saying is that the heat is negative, but remember heat is defined as increasing the energy of the system. So if the heat were going into the system, it would be positive. Here, we're saying that it is negative. That means heat is coming out of the system. So anything that makes the surroundings warmer is an exothermic reaction. On the other hand, if delta H reaction is positive, then the reaction is called endothermic. So you need to know the definitions of exothermic and endothermic. In other words, heat is a reactant of the reaction. We can think of it as being put into the system. Again, this is just saying that Q is positive, and Q is positive by definition when the energy of the system is increased. Now, the actual quantity of heat is a characteristic reaction for each characteristic value for each reaction. When I say characteristic, what I mean is that each different chemical reaction is going to have its own amount of heat that it gives off or that it takes in, and that's due to, again, the heat always comes from the making or breaking of chemical bonds in the reactants and products. That's what generates the heat difference in a chemical reaction. It's going to be very useful for us for manipulations of enthalpy values to learn 3 basic rules for manipulating enthalpy change quantities for chemical reactions. So first of all, keep in mind enthalpy is an extensive property. In other words, if more stuff reacts exothermically, then more heat is produced. And we know this sort of intuitively. You all know that if you burn twice as many logs in the fireplace, you're going to generate twice as much heat because you've burned twice as much stuff. That's really all we're saying when we say enthalpy is an extensive property. But what it means when we write down chemical equations is that if the enthalpy change for a given reaction, say the combustion of methane, if I write it in this form, if the enthalpy change is minus 802 kilojoules per mole, then if I multiply all of the coefficients by 2, which simply means that I'm burning twice as much stuff, then I necessarily have to multiply the enthalpy change by 2 because burning twice as much stuff generates twice as much heat. The next rule is that if you reverse a process, you have to change the sign, notice the minus sign here, of the enthalpy change. And this just is equivalent to saying, all right, if freezing water to make ice gives off heat, then it is necessarily the case that melting ice must require putting in heat. If you change the order of things, it changes the sign. Think of our analogy with elevation. If driving from Spokane to Seattle, you lose 2,000 feet, the elevation change is negative 2,000 feet, then it must be the case if you turn around and drive from Seattle back to Spokane, the elevation change is exactly the opposite, positive 2,000 feet. Again, that's all we're saying here with this property of enthalpy. And in terms of writing chemical equations, if we reverse the order, if we take this equation and make the products in this equation, the reactants down here, and the reactants up here, we make those products, we reverse the whole thing, we have to change the sign on the enthalpy change. Now notice, by doing this, we're not saying that this reaction can actually occur. We're really saying a hypothetical. If this reaction were to occur, then this would be the enthalpy change, because it's the opposite of this reaction. Finally, in the case of thermochemistry, it is really important to pay attention to the physical states of reactants and products. I didn't emphasize it as being super important when we covered equations in Chapter 3, but in Chapter 5, when we look at energies, they're very important. So, for example, if I write this equation, looks like the combustion of methane up here, but now notice I've made my water in the liquid state. I have a different enthalpy change for this because water in the liquid state is a different state than water in the gas state. And in fact, The difference is exactly the amount of heat to convert between water in the gas state and water in the liquid state. We all know it takes energy to boil water, so it makes sense that if we have water in the liquid state, that's going to change the energy in a chemical reaction.